Hello everybody, in today's video we're going to do a few step-by-step examples on titrations and buffers. Stay tuned.
Alright, so in this question we're told to calculate the hydrogen ion concentration and the pH of the solution, and we're given the values of hydrogen fluoride as 0.2 molars, we're given 0.1 molar hydrogen chloride, and the Ka for hydrogen fluoride is going to be 6.8 times 10 to the negative fourth. So the first thing that we can do is write the dissociation of hydrogen fluoride. Now, this being a weak acid, it's not going to completely dissociate, so that's why we write those two arrows going both ways. That means it's not going to always dissociate 100% of the time. Now, we're just going to write our ice chart. This is what we're going to use here. Now, we can start with our initial concentrations that were given. So we know we have 0.2 molar of hydrogen fluoride, that's given. And we have 0.1 molar of hydrogen chloride. Now where can we put that? Well, we know that the hydrogen chloride, being a strong acid, is going to completely dissociate. And that means that we have a 1-to-1 ratio of hydrogen and chloride. When it dissociates, we'll have 0.1 molar of hydrogen. We'll also have 0.1 molar of chlorine. So we can write our initial hydrogen concentration as 0.1. That's perfect. Fluorine, we got nothing. Still don't know what that is yet. So for our change, we're just going to denote that as x, because we don't know what that change is yet. So as this subtracts by s, these are going to increase by x. And at equilibrium, we'll just write 0.2 minus x. This will be 0.1 plus x, and this will just be x. Now, we have our equilibrium concentrations denoted as x being added or subtracted by something. That's really what we're interested in. So I'm just going to erase our I and the C in this chart, because all we're interested in is using our equilibrium concentrations, because that's what we need when we're going to write our Ka formula. So remember, the Ka formula is equal to the concentrations of products over the concentrations over the reactants. The concentrations at equilibrium. That's why we still want these. So we know that Ka is 6.8 times 10 to the negative 4. We're given that amount. Now we take the concentrations of the products, hydrogen and fluorine, and we multiply them. So when we multiply these, we'll get x squared plus 0.1x over concentrations of the reactants at equilibrium. This is just going to be 0.2 minus x. Now, this does not look like a very good formula that we have. So what we're going to do is we're going to rewrite it and get it into the quadratic formula, where we have ax squared plus bx plus c is equal to 0. So let's go ahead and rewrite this formula. Alright, so when we go ahead and plug this into the quadratic formula, we have our ax squared. A is just going to be 1 because there's nothing in front of it. Our b is going to be this value here. And then our c is going to be negative 1.36 times 10 to the negative fourth, since it's being subtracted. And when we plug that into our formula, it's going to give us two x values. And we remember which one to use. We're never going to use that negative value, because we can't start with nothing and subtract something if we have nothing to begin with. So we know that our x value is going to be this first positive one, 0.00133. What can we do with that? Well, we all know that our equilibrium is 0.2 minus x, hydrogen fluoride, and we're just going to plug this x into our equilibrium constants here. So our 0.2 minus our x, 0.00133. This is going to give us our concentration for hydrogen fluoride at equilibrium. That's going to be 0.19867. hydrogen ion concentration at equilibrium is 0.1 plus 0.00133. When we do that, that'll give us 0.10133. Then our fluorine concentration is just X. So we can write 0.00133. Perfect. Now that we figured out our concentrations at equilibrium, we can use these values to find the pH. In that first question that we were told to find the concentration of hydrogen, we found that. That's our first answer. So now this is what we're going to use to find the pH. So remember that pH means the negative log of our hydrogen concentration at equilibrium. So let's do that. Let's do negative log of our concentration, 0.10133. 0.10133. That's going to give us our pH of 0.994. That's our final answer for our pH value. Alright, in this question we're told to find the pH of a solution that contains 0.2 molar hydrogen fluoride and 0.1 molar sodium fluoride. And we're given the same Ka value for our hydrogen fluoride. So this looks like a very similar question to the one that we did before, but we're going to use a very different technique now. So the first thing that we should recognize is our two substances given here. Sodium fluoride is going to dissociate into a sodium ion and also a fluorine ion. So we should see we have hydrogen fluoride and then we have a fluoride ion. That means that this weak acid is going to be mixed with its conjugate base. So if we see that we have an acid and we're also mixing it with its base, conjugate base, we can use the Henderson-Hasselbalch equation and we can avoid the whole ice chart setup. So this equation states that the pH of a solution is going to be equal to the pKa, or acid dissociation constant, plus the log of our concentration of the base over the concentration of the acid. So we can use this formula to find out the pH if we're given an acid and its conjugate base. So we have everything that we need. So let's start plugging things in. pKa, we remember the P literally stands for negative log. The negative log of our Ka is 6.8 times 10 to the negative 4 plus the log of concentration of our base, 0.1, over the concentration of our acid, 0.2 hydrogen fluoride. So now that we have all of our values plugged in, we can go ahead and start simplifying, and we'll see what our pH is when we get this figured out. Alright, so now that we have everything simplified, we get as our final answer a pH of 2.87. Now this is how we find the pH when we're given a weak acid and its conjugate base form, utilizing the Henderson-Hasselbalch equation. Alright, so now I want to talk about some rules for determining if two substances can make a buffer solution. So the two main things that we need to look at is make sure that those two substances are weak acids and weak bases. So we can't be mixing strong acids and bases. Because if we mix a strong acid with a weak base, that acid is going to overpower the base, decreasing pH. The same thing with the base. If we have a base that's much stronger than the acid, we're going to increase the pH. And the whole point of a buffer is for the pH to remain kind of in that zone and not increase too much and not decrease too much. Next thing to look at is to make sure it's its conjugate form. So we have an acid, we want to make sure we're mixing it with its conjugate base and vice versa. So let's look at a few examples that we have here. Hydrochloric acid and sodium chloride. So let's look at these rules. Is it its conjugate form Well, here we have the acid, true, and here we have its base form. However, we should all realize that hydrochloric acid is going to be a strong acid. So this is why these are not going to form a buffer. Hydrochloric acid is going to be too strong. Now let's look at acetic acid and ammonia. Well, are they both weak? Sure. They're not super strong acids or bases. However, is this the conjugate form of one another? No, these are completely different things. So these aren't going to form a buffer. So let's look now at NaH2PO4 and NaHPO4. So these two being weak acids and bases is good. So we're going in the right direction. Is it its conjugate form? Well, let's look here. This first one has 2 hydrogens, and this one only has 1. So this would mean that this is its acid base, this acid form. That acid, donating one of its hydrogen protons, is going to leave us with NaHPO4, making this its conjugate base. So this is true. Perfect. Now let's look here. KNO3 and NaOH. KNO3 is going to be neutral. So it's not an acid or a base, meaning it's not going to affect the pH. And sodium hydroxide we know is a strong base. This is going to be too strong. Strong. This is going to be too strong. So we have something that's neutral, and we add a super strong base to it. That's just going to increase the pH too much, not giving us a buffer solution. Right, here we're told to find the pH in this question of a solution, a buffer solution, of 0.12 molar lactic acid and 0.1 molar sodium lactate. So now that we know that we're dealing with a buffer solution, since we have the acid form and its conjugate base, we can go ahead and skip the ice chart and use the Henderson-Hasselbalch equation. If we remember what that means, that basically tells us that the pH is equal to the pKa plus the log of that base concentration over the acid. So the first step is recognizing that we have that acid in its conjugate base. So let's just fill this in. This is simple enough. We did this one already. So the pH is equal to the pKa, means negative log, our Ka we're given as 1.4 times 10 to the negative 4th plus the log, our concentration of our base, sodium lactate, 0.1 over the concentration of our acid, lactic acid, over 0.12. That's going to give us our pH. So if we plug that in, log of 0.1 divided by 0.12, that gives us negative 0.079. And then the negative log, because we know that P means negative log, of 1.4 times 10 to the negative 4th is going to give us 3.85. Just subtract that, and then we'll get our answer for our pH. So our pH now is 3.77. So you can see that this is a lot quicker and a lot more simple than having to use an ice chart. We could also use the ice chart for this. But if we recognize that we have an acid and its conjugate base, it's much easier, much more simple. If we see that, and we know to use the Henderson-Hasselbalch equation. Alright, in this question, we're told that a buffer is made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate. And it makes enough water to make a 1 liter solution. So let's just start now by writing down our values. So we know that the volume is going to be 1 liter. And the pH of the buffer is 4.74. Alright, pH is 4.74. So we want to know what happens to the pH of the solution if we add, what happens if we add 0.02 moles of sodium hydroxide. And we're told that the Ka value is 1.8 times 10 to the negative fifth. 1.8 times 10 to the negative fifth. Alright, so this is all the information that we're given to us. So the first thing we should recognize is we have acetic acid and sodium acetate. That means we have an acid and we have its conjugate base form. So the first thing we should think about is that Henderson-Hasselbalch equation. And that equation, part of it was adding, that last part of the equation was plus log the concentration of the base over the concentration of the acid. However, here we're not given concentrations, we're given moles. So first thing that we should do is convert everything to moles. But we want to know what happens if we add 0.02 moles of sodium hydroxide. So here's a cool trick that I figured out, is that if we're adding a base, sodium hydroxide, if we're adding it, we're going to add that amount to our base that we already have, and we're going to subtract it from the acid. So base is adding to the base, and it will subtract from the acid. And the same thing is switched around. If we were adding an acid, let's say, we would add this amount to the acid, take it away from the base. So here, since we have a base that we're adding to this solution, let's subtract it from our acid. So if we take 0.3 minus 0.02, our new concentration will be 0.28, and our new concentration of our sodium acetate, since we're adding a base to a base, we'll get 0.32 moles. So we still don't have the concentrations yet, but we know that the concentration is the amount of moles times the volume. So if the volume is 1 liter, it's going to be the same, 0.28 moles in a 1 liter solution. The concentration is going to be 0.28. So this is kind of redundant since we're multiplying by 1 anyways. So now that we have our values, let's find out what the pH is going to be when we add this sodium hydroxide. So let's start that equation. It's pKa. So that P, negative log, of our Ka value, 1.8 times 10 to the negative fifth, plus the log of the concentration of our base. Since we added 0.02 moles of a base to another base, it'll increase the amount of moles. And since it's 1 liter, it's going to be the same thing. It was 0.32 moles times 1 liter will give you a concentration of 0.32. So 0.32 is our concentration for the base, and we put it over the concentration for the acid. Since we started at 0.3, and we use the trick of, since we're working with a base, we'll decrease it, subtract it from our acid. So we'll get 0.28 as our new concentration for our acid. So let's plug this in and see what happens to our pH when we add that. Let's do negative log of 1.8 times 10 to the negative 5. That will give us 4.74, and then we add, what's the log of 0.32 divided by 0.28? 0.05. So what's going to be our new pH? Let's see. Let's see if this buffer solution was successful at keeping the pH close. So when we do that, our new pH value is going to be 4.8. That's going to be our pH when we add 0.2 moles of sodium hydroxide.
Thank you for watching. If you found this video helpful, or if you have any questions on what I should do next, please let me know in the comments below. Have a great day.